Ever wondered how far we can push the quantum mechanic approximations before they break down? Let's explore the turning point in a quantum harmonic oscillator and see how far you can go before errors creep in. And of course, with this approximation being WKB, the Airy functions definitely start to play a role. So, in this problem, 9.9, we want to consider a particle of mass m in the nth stationary state of the harmonic oscillator with angular frequency omega. Part A wants us to find the turning point x2. Part B, how far d could you go above the turning point before error in the linearized potential, equation 9.33, but with the turning point at x2 reaches 1%. That is, if v of x2 plus d minus v linearization of x2 plus d over v of x2 is equal to 0.01, what is d? Okay, and then in C, the asymptotic form of AIZ, so Airy's function for z, is accurate to 1% as long as z is greater than or equal to 5. So for what d in part A or part B, uh, for the d in part B, determine the smallest n such that alpha times d is greater than or equal to 5. For any n larger than this, there exists an overlap region in which the linearized potential is good to 1% and the large z form of the Airy function is good to 1%. So that's pretty cool. So why do we care? Well, this determines the exact accuracy of the model, and of course, if we're going to use approximations, knowing the accuracy limits on them are very important to us. But this leaves me with a question that kept coming up in my head was, well, what happens if we use a higher order approximation for the potential? Here we're using a linearized potential, but what happens if we use like a second order? At that point, we might not be able to use the Airy function, but it's still something fun to consider as far as if this would be more accurate. As always, don't forget about the PDF. Of course, I think the YouTube is being nicer now with the external linking, so I'll try to put it in the description. But if not, comment and I'll find a way to get that to you because this is something good to keep in your repertoire. And if you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or donating through Buy Me a Coffee, no account required. Your support means the world to me and helps keeps this journey going. So on that note, let's dive into this question. All right, so stop one. What we have to realize here is that there are no vertical wells or vertical walls, and we just have a turning point that we need to find. So to find that, we first need to recall that this turning point happens when we have V equals the energy level that we have pre-assigned to it. So with that, we have the potential for the harmonic oscillator in terms of 1/2 m omega squared x squared, and the nth state energy level, which is n plus 1/2 h bar omega. Now, as we see, a factor of omega cancel from both sides, thus leaving us with m omega over 2 x squared with n plus 1/2 h bar. Now we need to multiply the reciprocal of this to both sides to isolate x squared, and thus leaving us with 2 over m omega with n plus 1/2 h bar. Distribute that 2n so we can get rid of that 1/2, and then we take the square root to isolate the x. So we get that our turning point here is square root of 2n plus 1 h bar over m omega. Keep this in mind because we're pretty much going to work with x2 the whole time, and this is the definition that we will use. Moving on to stop number 2 then, well, in order to find how far above the turning point we can go, we must first construct a linearized approximation for this potential. And this comes straight from calculus where you have the modified slope formula where we use the derivative, or you can just reference equation 9.33 where instead of the turning point being set at 0, we have it at x2. So we have the potential at x2, the derivative evaluated at x2, and then x minus x2. So if we go ahead and start plugging in, we see that 1/2 m omega squared. Now this goes to x2 squared. Now we have to take the derivative of this and then evaluate it at x2. And we see that via the power rule, we have a 2 here that'll cancel with the 1/2 out front. And then we can just plug in x2 and we'll be fine. And then we just keep this x minus x2. So what we can say here is that the linearized potential is 1/2 m omega squared x squared, or x2 squared, plus m omega squared x2 with x minus x2. Nothing too difficult here, but be aware that these coefficients on the x2 are going to have to be factored out in order to simplify, so keep that in mind as we move forward. We now have to kind of put this in form for the error function. So what we need to do is evaluate this linearized potential at x2 plus d, because we want to know how far above the turning point we can go. So we need to add the distance d with the turning point itself. So if we plug this in, we see that it only really affects the x minus x2 part from the linearized potential, and we see that x2 and x2 cancel, leaving us graciously with just some distance d. Okay, so we don't have to expand that out and make it look choppy and ugly, so we're good to go. But because we have a 1/2 m omega squared and a little bit of hindsight, it'll behoove us to go ahead and try to factor a 1/2 m omega squared out of both terms. So we're going to multiply by 1 to this latter term, and we'll turn that 1 into a 2 over 2. Therefore, we can factor out a 1/2 m omega squared from both terms, leaving us with x2 squared plus 2x2 times d, and that'll help save us time in just a second, I promise. Now, the potential above the turning point is x2 plus d, so we just have to put that in to 1/2 m omega x squared. So now we can FOIL this out and expand it, leaving us with x2 squared plus 2x2d plus d squared. And now we can go ahead and plug this into the error function. So the error formula now reads, well, if we want 1% over, we change that to a decimal, so we're good to go. And as promised, highlighted in blue, we have a factored form of 1/2 m omega squared with the potential at the turning point plus d minus the linearization at the turning point plus d simplified. And we see that we have over the potential at the turning point. And as you see, everything has a blue term in it, so we can factor that blue term out, cancel numerator and denominator. In factoring out the blue terms from the numerator, we see that we can combine all the arguments to one thing, and the x2 squared plus 2x2d from the potential cancel out with the linearization arguments, which is actually kind of really nice. And then we see we just get d squared over x2 squared. Both terms are squared, so take the square on the outside. This tells us explicitly that we need to take the square root now. So we get d over x squared is equal to the square root of 0.01, which, just a reminder, this is 10 to the negative 2. So get rid of having that negative 2 to negative 1, gives us 1 over 10, so 0.1. And then if we want to multiply over the turning point, we show that d has to equal 0.1 times the turning point. So pretty darn cool. And this is probably expected if we think about it. If we have a square potential, something like the harmonic oscillator where we have x squared, the square root to keep it in 1% makes plenty of sense. So this is falling in line with what we would expect, and that's pretty cool to see. The cancellations are very nice, and that just helps us solidify the algebra, but this definitely makes sense on the abstract level. So now we can move on to part D and find out what we want with the Airy functions. And this leads us straight to stop number 3. So if we want to determine the smallest n such that alpha times d is greater than or equal to 5, we need to visit our old friend, equation 9.35, which was the alpha substitution. Now in the book, again, they used v prime at 0 because we shifted the coordinates to where the turning point was at 0. But here we just have it at x2. Now remember, this substitution was used to turn the Schrodinger equation into the Airy function or the differential equation for the Airy function, and that was very cool. But now we have to actually plug in what our v prime at x2 was, and that was m omega squared x2, and thus we're left with 2m squared omega squared h bar squared times x2 all to the 1/3. So if we plug this into the inequality that we have up here, we get the alpha modified with the distance d now, which was 0.1 times x2. And again, we have to keep this greater than or equal to 5 for the accuracy argument. So noticing here that we have just a number here, let's go ahead and divide that over immediately. And since that was 5 over 0.1, that leads to 50. And now our whole task is simplifying this inequality, and that's nothing but a bunch of algebra. So let's go ahead and zoom through that. Wonderful. So with that, we saw that we had a 1/3 power, so we need to cube every argument. So cube this to get rid of that 1/3 power. That leaves us with an x2 cubed, and then 50 cubed is this large number, 125,000. We see we have a 2 up here, so let's go ahead and divide that to both sides. Combine x2 and x2 cubed, that gives us x2 to the 4th. So 125,000 divided by 2 gives us 62,500. No big deal. We see we have this turning point to the 4th power. So if we substitute in what we found from part A with the square root, we see that the square root will take off half of the 4th powers, but we're still left with the square left over. So hence we have 2n plus 1 squared, h bar squared, m omega both squared, but that cancels perfectly with what we had from the alpha substitution from the Schrodinger equation, so get rid of that. All of those cancel, and it's actually really darn cool. And from here, we can simplify pretty quickly. So what we're left with was 2n plus 1 squared has to be greater than or equal to 62,500. Take the square root, clearly follow the color coordination. That leaves us with 250. Minus 1 leaves us with 249. Divide by 2 leaves us with 124.5. However, since n has to be an integer, the minimum here would be the ceiling function of this half integer. So we would have to have n min is equal to 125, and that is the minimum n that we would need. Now, we say that the WKB method, and we read about it all the time, that it's for large n, and, okay, presumably so, but in 9.7, we saw how it was really highlighted that this may be valid for much smaller n. In fact, we had 3 significant figures of accuracy with n equal 2 in 9.7 when we had a linearized potential anyways due to V equal mgx for the gravitational potential. So we actually saw that this could work smaller, but it's still best in regimes where n is much bigger. And again, as we saw in a previous video, I believe 9.8, or yeah, maybe it was 9.72, but we saw that for n to be transferred to the microscopic scale, it had to be something really, really large, or from microscopic and macroscopic, the scaling, n had to be so humongous that it was brain hurt. So keep in mind that although this works for a larger n, the n being large is still artificial and needs more context. So keep that in mind. All right. That was not too bad of a question. It was actually really fun to see how accuracy of the models come into play. So I'm glad that we were able to cover that. That was really fun. Keep in mind though, again, n can vary from context to context, but otherwise, nothing too bad. I do want to give a massive thank you and a shout out to all the supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to the supplemental material, current and future projects, and one-on-one help. I know the new semester is starting this week, so definitely get ahead of the game. If trouble is occurring or if you're worried about a class, reach out. We like to help. It's a lot of fun. That being said, books, notes, and other reference materials are found below. If you're in the Instagram group chat, Please keep in mind that there's plenty more resources coming to you because I find a whole bunch of cool resources while I'm finding or making solutions to these questions. Excuse me. So keep in mind that is another avenue to get resource if you don't have enough yourself. There's always another online resource available. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.